Supernovae are among the most powerful and enigmatic events in the universe. For centuries, they've captured the imagination of astronomers and stargazers alike, appearing suddenly in the sky as brilliant points of light before fading into obscurity. Yet despite how bright and dramatic they are, the true mechanics behind these cosmic explosions remain frustratingly elusive. We know a great deal about the types of stars that end their lives this way, but the exact moment of detonation, that's still beyond our predictive reach. Part of the challenge lies in timing. Stars evolve over millions or even billions of years, but the final moments leading up to a supernova unfold in a matter of seconds. From our vantage point on Earth, catching that precise instant is like trying to photograph a lightning strike without knowing where or when it will happen. Because of this, much of what we know about supernovae comes from studying their aftermath, the glowing remnants scattered across space long after the explosion itself has faded. These remnants carry clues, but they're incomplete, distorted by time and interaction with surrounding material. Occasionally, astronomers get lucky. A telescope happens to be pointed in the right direction at just the right time, catching the early light of a supernova as it begins to brighten. But these moments are rare and often still too late to reveal the earliest phases of the explosion. The initial geometry, the true shape of the blast as it begins, is quickly erased as expanding material collides with gas and dust in the surrounding environment. But recently, something changed. For the first time, astronomers managed to intentionally capture a supernova almost exactly as it began. Not days later, not even a full day later, within hours. This early detection opened a completely new window into the physics of stellar death, revealing details that had never been directly observed before. Most importantly, it allowed scientists to measure something that had remained hidden until now, the shape of the explosion itself. At first glance, that might not sound revolutionary. Shape doesn't seem like the most exciting property compared to brightness or energy. But in astrophysics, geometry is everything. The shape of an explosion carries within it the fingerprint of the physical processes that created it. It tells us whether the blast was smooth or chaotic, symmetrical or distorted, driven by internal pressure or focused jets of energy. To understand why this matters, we need to step back and look at how massive stars live and die. Stars spend most of their lives in a delicate balance between two opposing forces. On one side, gravity pulls all the star's material inward, trying to collapse it into a dense core. On the other, nuclear fusion in the core generates enormous amounts of energy, creating outward pressure that resists this collapse. As long as fusion continues, the star remains stable. Inside the core, lighter elements are fused into heavier ones. Hydrogen becomes helium. Helium becomes carbon. Carbon transforms into oxygen, and so on, progressing up the periodic table. Each stage releases energy, sustaining the star against gravitational collapse. But this process cannot continue indefinitely. Eventually, the core begins producing iron. Iron represents a dead end in stellar fusion. Unlike previous reactions, fusing iron into heavier elements does not release energy. It requires energy. This means the star can no longer generate the pressure needed to counteract gravity. When the core becomes dominated by iron, the balance is broken. What happens next is catastrophic. With no outward pressure to support it, the core collapses inward at incredible speeds. Matter accelerates toward the center, reaching a significant fraction of the speed of light. Temperatures and densities skyrocket. Protons and electrons are crushed together to form neutrons, and a flood of nearly massless particles called neutrinos is released. Then something remarkable occurs. The collapsing material slams into the dense neutron core and rebounds, sending a shock wave outward. This core bounce should, in theory, blow the star apart, but in practice, the shock wave often stalls. It loses energy as it plows through the dense outer layers of the star, breaking apart heavy nuclei and dissipating its Shakti. This is the critical moment. If the shock wave cannot recover, the collapse continues, and the star may form a black hole without ever producing a visible explosion. This is known as a failed supernova. But if the shock wave is somehow revived, if it gains enough energy to continue outward, the star explodes in a brilliant supernova. The question is, what revives the shock? For decades, scientists have debated this. Two leading ideas have emerged. The first involves neutrinos. These particles, produced in enormous quantities during core collapse, carry away vast amounts of energy. Some theories suggest that a small fraction of this energy is deposited back into the surrounding material, heating it and creating turbulent convection. This added urja could push the shock wave outward again, triggering the explosion. The second idea focuses on jets. In this scenario, the collapsing core forms a rapidly spinning neutron star surrounded by a disk of infalling material. Magnetic fields become amplified by the rotation, channeling energy into narrow jets that shoot out along the star's rotational axis. These jets can punch through the star's outer layers, driving a highly directional explosion. Each model predicts a different shape. A neutrino-driven explosion would likely be messy and asymmetric, with no clear structure. A jet-driven explosion, on the other hand, would produce a more organized shape, elongated along a central axis, like a football or an olive. This is where the recent observation becomes so important. By capturing the supernova within hours of its onset, astronomers were able to measure the polarization of its light. Polarization reveals how light waves are oriented as they travel, and it can be used to infer the geometry of the source. If the explosion were perfectly spherical, the light would be unpolarized. But if the explosion were asymmetric, a pattern of polarization would emerge. The data showed a clear axis of symmetry. Instead of a chaotic, irregular blast, the explosion appeared elongated, consistent with a structured, directional mechanism. At first glance, this seemed to support the jet-driven model. But the story doesn't end there. When scientists simulate these processes in detail, complications arise. Neutrino-driven models often struggle to produce explosions with enough urja to match observations. Meanwhile, jet-driven models can become unstable in three-dimensional simulations, with jets wobbling and losing their alkudra to drive a clean explosion. So neither explanation is entirely satisfactory. This has led researchers to consider hybrid or alternative mechanisms. One intriguing possibility is that jets do play a role, but not in the neat, stable way originally imagined. Instead, they may jitter and wobble, depositing energy in different directions near the core. This chaotic behavior could still produce an overall symmetrical explosion while avoiding the smusyae seen in simpler jet models. In other words, the explosion might be both structured and chaotic at the same time. This new observation doesn't solve the mystery of supernova, but it dramatically narrows the field of possibilities. It tells us that whatever mechanism is responsible must be capable of producing organized symmetry, even if the underlying process is complex and unstable. And perhaps most importantly, it proves that we can capture these events in real time. With new sky surveys and increasingly powerful telescopes coming online, astronomers are entering a new era of transient astronomy. Instead of passively waiting for supernovae to appear, we can actively monitor the sky, detecting changes as they happen. By comparing images taken just hours apart, we can identify new explosions almost immediately and follow them from their earliest moments. This capability will transform our understanding of stellar death. Each new detection adds another piece to the puzzle. Some explosions may show symmetry, others may not. By building a large sample of early observations, scientists can begin to identify patterns, linking different explosion shapes to different physical mechanisms. Ultimately, this will help answer some of the oldest questions in astrophysics. What causes a star to explode? Why do some stars fail while others succeed? How do the most extreme environments in the universe behave under conditions we cannot replicate on Earth? These questions are no longer purely theoretical. They are becoming observable. The universe is constantly evolving, and for the first time, we are starting to witness its most dramatic ghটনায় as they unfold. Not as distant echoes from the past, but as real-time events that we can study, analyze, and understand. Somewhere out there, right now, another star is reaching the end of its life. Its core is collapsing. A shock wave is forming, and within moments it may either fade quietly into darkness or erupt in a blaze of a dough visible across millions of light years. And this time we might be watching